Hello and welcome to the second part of the tutorial. In this part, I will discuss about various issues regarding training of restricted Boltzmann machine. This part is little bit mathematical, but hope you will easily understand it. In this tutorial, I will try to derive the equations to train the restricted Boltzmann machine. Suppose we have a simple restricted Boltzmann machine with visible units V1, V2, V3, V4 till Vn and hidden units H1, H2 till Hm. We have a bias known as C attached with all visible units and single bias attached with B1, B attached with all hidden units. Now, the joint configuration of visible and hidden units can have the energy and represented as EVH, and it can be given by these equations. This is equal to sum of product of all visible units and attached bias, all hidden units and attached bias, and sum of product of all visible units, hidden units and their weight. So here you can say that Vi represents the ith visible unit, Ci represents ith bias attached with visible units V1, Vi. Similarly, Bj is the ith bias attached with hidden unit Hj, and Wij represents the weight between ith visible unit and jth hidden unit. So W11 will be here the weight between V1 and H1. Now here, as we represent single bias for all visible units and single bias for all hidden units, so it may be like C or B, not Ci and Bj. Now we can use this energy equation to represent the probability distributions between visible and probability distribution of visible and hidden units. Here Z is the summation over all possible connections between two layers, also known as partition functions. So in this case, suppose we have in this case Z will be equal to e to the power minus e V1 H1 plus e to the power minus e V1 H2 till e to the power minus e Vn Hm. So the main purpose of this Z, also known as partition function or normalization constant, is to make sure that sum of the entire probability distributions will be equal to 1. Now, how we can assign the probability to visible units? We can assign a marginal probability of visible unit input vector, say V. And it can be calculated by summing over all the hidden units. For example, marginal probability for V1 will be equal to the normalization constant and the sum of like e to the power minus e V1 H1 plus e to the power minus e V1 H2. So in this case, and similarly and here Z will be equal to e to the power minus e V1 H1 plus e to the power minus e V1 H2 plus e to the power minus e V4 H2, as we have V4 till H2. So this will be equal to Z and this will be equal to the value, marginal probability value for V1. Similarly, we can calculate the marginal probability distributions for H1 and H2. Now, as I stated earlier, that in a restricted Boltzmann machine, there is no connections between two visible units or two hidden units. Means, in other words, we can say that RBM has a shape of bipartite graph with no intra-layer connection. Means visible unit activations are mutually independent given hidden units activations, and similarly hidden unit activations are mutually independent given visible units. So in the case of mutually independent, we already know the use of product of probability distributions. So here in the current case, the conditional probability of V given H can be computed by using the product of I is equal to 1 to n, and similarly the conditional probability of H given B can be calculated by product of conditional probability from J is equal to 1 to m, where J represents the Hj represents the jth state of hidden units. Now the next part is in the case of RBM with binary units, where visible and hidden units value are either 0 and 1. We have the following. We can identify this kind of probabilistic distributions. Means conditional probability of Vi equal to 1 given H can be given as sigmoid of the attached bias plus sum of product of attached hidden units and the weight with Vi. We can understand it simply like that. Conditional probability of V1 equal to 1 given H can be given as sigmoid of V1 plus H1 into W11 plus H2 into W12. So this is H1 and W11 represents this weight, and this is H2 and W12 represents this weight. So this is the conditional probability, and the sigmoid is same that we generally use in ANN based computations. So only this part is slightly similar to the artificial neural network. Similarly, the conditional probability Hj equal to 1 for all given attached visible units can be given as sigmoid of attached bias a plus sum of all visible units attached with that hidden unit and the corresponding weight that I calculated in this case. So these are the basic assumptions that will be used in the training algorithm, in the derivation of training algorithm. Now let us start deriving algorithm by using the probability assigned to the visible units. We already discussed this probability here earlier and represented it as a marginal probability of visible layer. So now how to derive the learning equations through this probability? Actually, restricted Boltzmann machines are Markov random field with hidden variables, and RBM learning algorithms are based on the gradient ascent on the log likelihood. So we take a model with parameter theta, the log likelihood for a given simple training example B, then it can be written as in slightly different format like that. So we can represent these equations, and this part is changed like that, and again we can represent this as these equations. After simplification we get these two parts. So now the question is, why log likelihood with a gradient ascent? Actually, natural logarithm is a monotonically increasing function. This means if the value of x-axis increases, the value of y-axis will also increase. And this ensures that the maximum value of log of probability occurs at the same point as the original probability function. Therefore, it makes the work more simpler with log likelihood instead of original likelihood. That's why we take the log likelihood. So now let us start the derivation. Actually, in the derivation, so we derive this part here and we take the derivation for this part here, and after applying the some derivation skills we can get these two parts, and finally after simplifying we get this. Now we take the log likelihood of single training pattern V with respect to weight like Wij. Why? Actually, when we train any network, the training of any network means either artificial neural network, deep neural network, convolutional neural network. The main purpose of this training is to learn the weight of those connections. Means we have to learn the weight, optimal weight of those connections, so that when we provide the some inputs through visual layer, we get some outputs through some latent relations. So this is the main reason. For that we take the derivation with respect to Wij. Similarly, to change the or identify some changes in the bias factors, we take the derivations with respect to bias also. So now let us start with weight factor. So taking the derivations with respect to Wij, so this part comes here and this part comes here, and after derivation, taking derivations, it can be simplified like this part and this part. Now again further simplifying, we will get this and this part. Now suppose we have a training set with visible units V1 to Vn, then we can take the average of sum of all such derivations, and then this will be equal to and finally when we solve it, it will comes into two different forms. We already know that such kind of conditional probability we can learn through very simple equations, but here it represents the joint probability of the entire structure or model. So I think we can simplify it, the entire equations, like that, and this is proportional to expectations of outer products of two vector Vi and Hj, visible and hidden units, with respect to input data, and expectations of visible and hidden units with respect to the models, with respect to the model. So this is the sign, this bracket sign represents the expectations. So now let us learn what is expectations, what will be the further step to get quick learning. So in a very simple format, we can represent this part as a derivation of log p for all visible layers with respect to weight Wij, and this part is equal to data, and this part is for model. So before going into the detail, let us go through the concept of expectations. For this I have used the Wikipedia reference. Let x be a random variable with finite number of outcomes x1, x2 to xk, occurring with probability p1, p2 and pk. The important part is that sum of all probabilities values equal to 1. So the expectations of x can be given as Ex is equal to sum of product of outcomes into their corresponding probabilities. Now, how to use this concept in the current expectations format? This will give you some estimate like what may be the further directions for training, whether we can get all those expectations quickly or we have to apply Gibbs sampling. This will also answer that why we are using Gibbs sampling in training of restricted Boltzmann machine. So now let us go through some issues with while training using this format. Now to calculate the expectations of fx based on the probability of px, we use this format. This is similar to this format, and here we can simplify the Vi expectations of outer products of Vi and Hj with respect to model as Vi and Hj with respect to joint probability of visible and hidden states. Thus the model part PV at probability of visible and hidden states contains the probability of all states of visible and hidden nodes. So in this case the total number of nodes states will become 2 to the power total number of visible states plus total number of hidden states. Now suppose an RBA machine having 1000 visible units and 500 hidden units, then in that case total number of states will be equal to 2 to the power 1500. With the increase in size, it will be too costly to calculate, because this part is coming from data, so we can easily calculate, but this part depends totally upon the structure. That's why we are applying some sampling based approach named as Gibbs sampling. So now let us see how Gibbs sampling works and how many steps that we have to go for sampling. So actually Gibbs sampling, suppose this is a state transfers at different iterations at t is equal to 0, t is equal to 1, t is equal to 2. So suppose we are going till infinite number of iterations. So in the first iterations, how we can go, start with a training vector, suppose of a visible unit vi, and by using that visible unit vi, we will calculate the value for all connected hidden units, h1, h2, all connected hidden units. And again, by using those sampled hidden units value, we will update all the visible units again for all the iterations. And again, using the sampled visible units, we update the hidden units again. So this is the process that goes in Gibbs sampling. So it is believed that after few samples we can get a certain accuracy. So this is achieved that this is the first iterations by using data, and then we can get the reconstructions at time t is equal to 1. So change in weight is generally believed to be equal to that epsilon some learning rate, and this minus this, because it is assumed that this part is very close to that infinite part. This is stated in the some latest papers. You can check for reference section. I have attached some papers in reference sections for more information on these issues. Now we can simplify this part like that. The derivation of log p v0 with respect to weight wij can be simplified like v1 till v infinity, and this will be equal to this. So same thing is stated here. Now just summarizing. Suppose we have n training examples. In RBM, and as RBM is a stochastic model, so the outer product need to be averaged against the probability distributions. So for n training case, we take this derivations will be equal to the average of summations of this difference. Here VIN is the value of ith visible unit for nth training case, value of jth hidden unit for nth training case. This is the sampled value for ith visible units or negative phase generated on hjn and wij. Similarly, this is the sampled value of jth hidden unit. So for each training example, we will calculate this and replicate here. For n equal to 1, this will be simple, and for n equal to n, so for each value we will calculate such kind of trainings.